Hello everyone and very good evening. Once again, welcome back to interview preparation session. So let's begin with different set of questions. Okay, first one, what is regression? And types of regression? So how can we explain regression? And what are the types? So when we talk about the regression analysis, it is a form of predictive modeling technique which investigates the relationship between an independent and dependent variable. So the same technique we are using even for forecasting, right? I can say the time series modeling, and we are trying to find out the cause and effect relationship between the variables. So there are multiple benefits of using regression analysis. The interpretation of each and every component of regression helps us to give better accuracy than any other model, machine learning models. So it indicates the significant relationships between dependent variable and independent variable. It also talks about the strength of the impact of various multiple independent variables on dependent variable. So what are the types? Many types are there, right? We can talk about lasso, ridge, stepwise, polynomial, logistic, and very famous linear regression. All these are types. So now, if we discuss something about the linear regression, what are the things you can cover under linear regression? So it's one of the most widely known modeling techniques. It is usually among the first model where we deal with y being continuous, right? You have y being continuous, but x can be discrete or continuous. And we are interested in the best fit line, or you also call it as regression line. So the regression is, this linear regression is trying to establish a relationship between dependent variables and one or more independent variables using a straight line, which is a best fit straight line, the so-called regression line. So we are interested in equation of a straight line, and that equation of a straight line is mx plus c. Added to that, you have the error component added, where your c happens to be the intercept, m is the slope, e is the error term. So if at all you have one variable which is input, you call it as simple linear regression. If you have multiple variables, you call it as multiple linear regression, more than one independent variables, right? So how do we obtain the best fit line? How do we obtain best fit line? What is this here? So the task can be easily completed to get the best fit line using the concept of what you call it as ordinary least squares method. It's the most common method used for fitting your regression line. It calculates the best fit line for the observed data by taking into consideration the minimizing the sum of the squares of your deviations in a vertical manner for every data point to that particular line. So because the deviations are squared when added, there is no cancelling between your positive and negative values. We can evaluate your metric with R square. Right? So in this scenario, we check the line assumptions. So explain line assumptions. So what are line assumptions with respect to regression here? When we are talking about line assumptions, first we are interested in linearity. Your coefficients, that is nothing but y is equal to beta naught plus beta 1 x1, where beta 1 or beta naught, these are called as coefficients. You also call them as estimates. You also call them as the parameters. Right? So these should enter this regression equation line linearly. Right? Once you do your model building, you are getting your residuals, you are getting your fitted data. When you do a plot between these two, that should also be linear in nature. It should be linear in nature. Over to that, your inputs should have a linear relationship with output, right? But when we are talking about errors, which is the most important term for your regression equation, errors are also having some assumptions, right? Your errors should be independent. Your errors should be identically distributed. Errors should be identically distributed. Your errors should be normal. Normality check should be done for the errors. Right? What is the other error? If error should have constant variance. And finally, average of errors should be least. Right? These are the assumptions with respect to your errors. If your errors are having relationship among itself, if they are not independent, you are entering into a problem called as autocorrelation. If you are not independent, no constant variance, you are entering into a problem called as heteroscedasticity. So you should have the best accuracy, means all these assumptions should be satisfied. Right? So we can go with your model as successful model building happened if these assumptions are satisfied with respect to your errors. Not only assumptions with respect to this, you have assumptions with respect to predictors also. Predictors are nothing but your columns. You can also call them as features. Right? These predictors, columns, or features are also having assumptions. Right? When you have different inputs, all the features, they cannot be random. Randomly, whatever you have, you cannot take it. They should be non-random. right? If at all they are non-random and they don't have any relationship among themselves, they should be independent. One is nowhere related with the other. If x1 is having some relationship with x2, you are entering into collinearity problem. Provided if x1 is having relation with x2 and x3 and x4 also, you are calling it as multi-collinearity problem. This is called as multi-collinearity problem. So these are some things which you have to focus when you are selecting your features. Right? Collinearity is a major issue with the predictors. So when you have your observations also, observations are nothing but number of data points. They should be reliable. All the observations are equally important, not giving importance to any of the observation. Right? These are called as line assumptions: equal variance, normality check, independent, and linearity. So the main focus here is that for linear regression, y is equal to beta naught plus beta 1 x1 plus beta 2 x2, what you have. These are entering the equation linearly. Right? This is the main thing what we can see here with respect to this. But what if at all you have overfitting problem here for regression models? So we have different classification models. We have studied different regression models. We know different regression models. So what is a regularization technique for regression? So we also have bias and variance problems here. So we are going for regularization technique. So what is that? You have to remember, when you are going for naive-based classification model, the regularization technique you are following is Laplace, where this is solving the issue of zero probability problem. Right? They are taking zero probability problem. Then we have started one more classification algorithm, which is based on a lazy learner or distance matrix algorithm. K is a technique, regularization parameter to reduce your overfitting. Then we had decision trees classifier, where we had post pruning, pre pruning. We had post pruning and pre pruning. And when we started with boosting techniques or random forest, right, we had number of features, number of trees. Right? So many hyperparameters are there, number of estimators. Right? All what holds good for decision tree, they hold good for random forest also. You had bagging, we had boosting. Now we are into regularization for regression, which is your L1 and L2 norms. So what is it? What is that it is required here? The main thing, the main focus here is there is something called as R square and adjusted R squares. Right? You say that the model is good or bad with adjusted R square and R square. So what is this R square? And what is this adjusted R square? So how do you evaluate a regression model? Right? How do you evaluate regression model? You are calculating R square, which is nothing but, we say that it is the coefficient of determination. Right? So it is nothing but coefficient of determination. So it is nothing but the right fit, or I can say goodness of fit. So this value ranges from 0 to 1. So whenever we are working with R square values, when we are interested in R square helps us to know how well your model is predicting. Suppose R square happens to be some 0.5. It means out of 100 data points, 50 data points your model can predict properly. That is the goodness of fit. That is the goodness of fit. Here, when we are talking about this, let me, okay, should be there. So we are talking about goodness of fit. There is something which we have to understand with respect to R square, the disadvantage of R square. So you have something called as baseline models, right? For any given value of X, you get Y bar as your prediction. There is no question of input getting affected. It is called as baseline model. No prediction is happening here, which is baseline model, right? So when we talk about baseline models, your baseline model should work the worst, because given any inputs are not having impact on Y, just taking the average of this and you're saying Y bar is a prediction. X can be anything, Y is not changing, it is same constant. If Y is 1, 2, 3, 4, 5, average is 3, X is 1, 4, 5, 6, 8, 9, 10, 11, whatever might be the X, output only is this one. This is called as baseline model, right? So R square will become good, high, right? If your baseline model works the worst, right? Your baseline model will work best. So your predictions should be good. Your predictions should go good. Means your baseline model should go worst. Then only R square will increase. Higher the R square, better the model. Better the model. So in this scenario, when you keep on adding your inputs, when you keep on adding your variables, R square by default will increase. By virtue of its formula, it is going to increase. To analyze whether the given input variable is having effect on Y or not, it is important or not, it is least bothered. It will never bother. Right? It never bothers with that. So what will happen? You are adding one input variable. When you are adding this input variable, definitely R square will increase. If R square is increasing, you are feeling that yes, that is what your requirement is. So it evaluates. You are talking about the scatter of the data points around your regression line. So it is also called as coefficient of multiple determination, right? It is nothing but given by the formula variance explained by the model by total variance. Larger the R square, better the model. But it is having limitations that R square does not indicate if a regression model provides an adequate fit to your model. A good model can also have a low R square value. Right? A biased model can have high R square value. So sometimes low R square values also can be perfectly good models for several reasons. Right? So to penalize this effect, if R square keeps on increasing with different, if at all you get higher R square value, we are always happy. Right? So because of that, R square tends to increase if too many independent variables are there in the regression model. So what happens here? People have come up to solve the problem of R square with the help of adjusted R square. Adjusted R square will only increase if the added input to your data holds some value. right? So if R square is increasing and adjusted R square is also increasing, X4 is great. You can include in your data set. If R square is increasing, adjusted R square is decreasing, this is waste of including in your data. So to penalize the effect of added feature, we are looking into adjusted R square, and these both should be nearly equal to move forward with the added variables. So when you keep on going and you keep on adding your variables, a point comes where if at all you are having with only X1, your model is not able to learn patterns properly. So it leads to underfitting. So what will you do? You want to make it into right fit. So you add features. So what did you do? You added more and more features. So your learning is happening by your model, overlearning is happening, it is leading to overfitting. So there is a situation where you have to pull in with a right fit. There should be some balance. So you should not add more features, you should not have less features. Right features is what you have to check. For that reason, in regression, you are using regularization techniques, which are L1 and L2 norm. To penalize the effect of overfitting or the loss function, what we are getting, we are adding one penalty term here to the loss function so that we can reduce this or solve this problem of overfitting here. Solve the problem of overfitting. So assumptions is that same, that all the assumptions will hold good, but this is something what we are going to add as a penalty term to your loss function. So what is your loss function here? You are getting equation of a straight line. You have yi minus beta naught plus beta 1 x1. This is the error. This is your actual value minus predicted value. So to this actual value and the predicted value, which is nothing but the loss function or the cost function or the error function in regression, I should add the penalty term. So how do I add the penalty term? If at all I add the penalty term, that is nothing but the regularization parameter, what I'm adding it to the loss function so that my model will not learn too much. It will not leave the patterns also. So the right fit is what I'm trying to put it under this technique. So L1 or L2 now, these are the two where we call it as L2 as ridge regression, L1 as this one. So what you do here, actual value and number of observations you have, I is equal to 1 to n. For this, if I expand this, it will become I is equal to 1 to n. You have yi, I separate beta naught plus j is equal to 1 to p beta j xj. Right? On top of this, I have the square. Right? This is nothing but this equation is my loss function. This is my OLS technique. To this OLS technique, now I am going to add the penalty term, that is lambda sigma j is equal to 1 to p, right, beta j square. This 2 is nothing but my L2 norm, which is nothing but my ridge regression, which will make my estimates nearly equal to 0. So j is equal to 1 to p. It is nothing but my inputs are x1, x2, x3, x4. So j is equal to 1 to 4. Whichever input is having less impact on y, that will be deleted. It is not deleted, it is given least importance. It is equated almost to 0, not 0. This is called as, this parameter what I have added is called as shrinkage penalty term. This is called as shrinkage penalty term. So adding to this, right? So how do you are choosing your lambda value now? You are having your mean square error on the y-axis. You are having your lambda here. If you choose very, very low lambda, you have high variance like this. Your lambda is increasing. You are bringing down your variance. Variance is becoming like this, very low. In this fashion, when you do it, our other friend bias will increase like this. You're increasing. When lambda is 0, we are happy with this. This is my bias. This is my variance. What is happening? This is my, I don't want low bias, high variance. Low variance, high bias. I want the right fit. I want the right lambda. Choosing the right lambda will reduce the problem of overfitting. So lambda being your tuning parameter. Lambda is nothing but your tuning parameter. So you don't want high bias, high variance, low bias, high variance, low variance, high bias. All these three cases we don't want. The bullseye diagram. We want the right fit with the right lambda value. The other way around, if at all you're talking about your L1 norm, you are adding loss function plus sigma j is equal to 1 to p lambda. You are having your beta j magnitude, where beta j will be made 0. So that's why L1 norm is also called as feature selection algorithm. It is called as feature selection algorithm. So it directly beta naught plus beta 1 x1 plus beta 2 x2, it will make your coefficient equal to 0. Right? So this is called as a subset selection algorithm also. These are the two techniques. So you have one more, which is nothing but your elastic net. It is a balance between your L1 and L2 norm, which is called as elastic net. What is this elastic net now? It talks about the balance between your regression, right? Ridge regression and lasso regression. It tries to pull in the balance. So lambda is equal to the tuning parameter, which is helping us to solve the problem. So it is nothing but you will have your OLS technique. First, what is it? How do you write it? Yi minus sigma 1 to beta, your xj, your beta j whole square plus 1 minus lambda into j is equal to 1 to p beta j whole square plus lambda sigma j equal to 1 to p magnitude of beta j. So this is my lasso, this is my ridge, this is my OLS. Totally you call it as elastic net. In this equation, if you give lambda is equal to 0.5, it is elastic net. If lambda equal to 0, this gets cancelled. This will become your ridge regression. If you put lambda is equal to 1, 1 minus 1, 0, the rest of the equation will become lasso regression model. Lasso regression model. This is the regularization technique for regression analysis. Right? So the group of predictors are they are highly correlated, right? And it picks only them and shrinks the every other input variable to this, right? But sometimes we can say that it will also, this elastic net will suffer with something called as double shrinkage also, right? So how do you pick the right one? Is that is a tuning parameter. You can go for grid search technique so that you can run for different lambda values where this will solve the problem of overfitting, and you want the right fit with low bias and low variance. Where we are using logistic regression. Logistic regression. So whenever it is a binomial distribution, when it is 1 or 0 scenario, pass or fail, rain, no rain, cancer, no cancer, we are using logistic regression. And why being discrete? Why being discrete? Right? So to find the probability of an event which is a success and the event could be failure, we would use logistic regression when the dependent variable is binary. So y value is ranging from 0 to 1. Right? So it is very much, it is used for classification models, but the prediction happens with the numbers. The prediction is happening with the probability value. That is the reason we are putting it under logistic regression. So it is not having much relationship, much assumptions here with the relationship between the inputs and the outputs. It does not require linear relationship between your inputs and the output, that is dependent and independent variables. It because the transformation that is going to apply here, log transformation, to predict your odds ratio. So here also, to avoid overfitting or underfitting, we should include all the significant variables. And a good approach is that to ensure is to use your stepwise method to estimate the logistic regression. So when compared to linear regression, logistic regression requires more number of samples. That the independent variables should not be correlated with each other. However, we have the options to include the interaction effects or the moderation variables, right, in the analysis. If the values of the dependent variable is ordinal, then you will go for ordinal logistic regression. If at all the values of the dependent variables are nominal and are multi-class, multinomial logistic regression. So the main difference between the regression, which is y being continuous is linear and y being discrete is your logistic. So what we are understanding here, we are saying that everything happens with probability. Probability is the output here. So the probability in a logistic regression is given. For example, now we are saying that y is equal to beta naught for any regression equation. The estimates should enter this regression equation linearly, which is pretty common in linear regression. But when it comes to these estimates, here in logistic regression, they are not entering this equation linearly. They are non-linearly entering into this. So the main aim is to make these coefficients or estimates or parameters to enter the regression equation linearly, right? So people have come up with different equations. So they thought that probability value is something. Equation is anyway same. That is regression is regression. You have the equation here. But what is this calculation they are doing? They have substituted here in the y. You are getting the probability of whatever y you are getting, y hat, you are substituting it here. So how does it go? Your p is equal to e to the power of beta naught plus beta 1 x1 by 1 plus e to the power of beta naught plus beta 1 x1. This is called as logistic regression function. And the transformation you are applying is called as a logit transformation. The transformation you are applying is called as logit transformation. So instead of P, what people thought is this is not solving the problem of non-linear entering of this coefficients. They thought 1 minus P is what they have tried with. So when it was 1 minus P, it was like this. 1 plus e power y. This and this got cancelled. You are left out with 1 plus this. So they calculated odds like this, P by 1 minus P. P happens to be e power y by 1 plus e power y by 1 plus 1 by e power y. This got cancelled. Still, when they calculated odds, you are not getting y directly. It is exponential of y. You are left out with only y because you have cancelled P by 1 minus P. So finally, there were no other option for us to find out y. They took log of P by 1 minus P, which led to get y. So odds, log of odds is what you are calculating here to solve your y, which is nothing but your beta naught plus beta 1 x1. So whatever values you are getting, many functions like probit function is also there, but we are applying here logic function to solve this. You can also try with probit function also. So because of this, you are calculating odds, and log of odds is something which we are following here. But very important point with respect to our logistic regression here is how you are evaluating such models. What is the evaluation metric for logistic regression and linear regression? Are they same? Because it is regression, evaluation metrics what is the evaluation metric for linear and logistic? Or I can say for regression models. Why to separately taking this? For regression models, what is this evaluation metric for this? Okay, for linear regression. So mean square error is something what you can do, right? We are talking about the mean square error. What is the problem with mean square error for y being numeric, or I can say y being continuous? Mean square error is what we are taking. So the most popular is mean square error, but here what is happening, if at all you are having units, right? You have your actual value, you are dividing your predicted value, it's $1 minus $5, right? You are squaring it, $4, you are happy that you are getting 16, right? It is a dollars square. To counter this, we are not using mean square error, we are using root mean square error, which is a standard and the most important evaluation metric for y being continuous regression model. It follows an assumption that the errors are unbiased, and it will also follow normal distribution. The power of square root, it empowers the metric to show large number deviation. The squared nature of this metric, it prevents the cancelling of our positive and the negative error values. Right? It also avoids you to use this what you call as absolute values, error values. So which is very, very undesirable for rate of change option. For gradient problem, we are not using absolute value. So RMS is highly affected by outlier values, Hence, you have to make sure that you remove your outliers from your data set prior to apply this metric. Right? So RMSE is nothing but you are getting predicted value whole square. Sorry, my bad. Actual value whole square by n. So this is number of observations you have. It is the total number of observations. So if this is one thing, but people also say that correlation is something which is used here to find out how good is your model. And people also consider R square as well. Right? Just now we have discussed these two are also evaluation metrics for linear regression. So preferably mean absolute percentage error, mean absolute percentage error, and RMSE for linear regression. Yeah, that is other way around, that you have the absolute mean square error, right? Mean absolute deviation. Many other are there, but we are only using these three to evaluate your model for y being continuous. Now, how about when y is discrete? Is the same going to work? Is it going to work in the same way? If at all, we are talking about the error calculations for logistic regression or y being this thing. Here, though you are doing classification, right? Even though the calculations are happening with the probability values, the same metric we use for classification, we use here only. Right? That is nothing but cross table or confusion matrix. Right? It is nothing but a contingency table or contingency matrix which will help us to calculate the accuracy of the model. So how it is going to work? You will have your actual values. You will have your predicted values. If it is a patient is a positive cancer patient, negative cancer patient, positive and negative. Actual values and predicted values are same. Actual values and predicted values are same. These two are your errors. Right? So, however, you are calculating the accuracy with, this is called as, it is true actually. Your predictions also are saying true positives. So your actual value is positive. Your predicted value is also positive. So you call it as true positives. Right? Here, your actual value is negative. Your predicted value is also negative. So it is nothing but a true negative. Okay? So these two. If you add these true positives plus true negatives by total, all the other two, which are errors, you are getting the accuracy. But what is that you have to focus here? The proportion of total number of predictions which are correct is this. So the positive predicted value, negatively predicted value are something what we have to focus. So there's something called as cost-based relationship or analysis, which will help you to decide and say the model is good or bad. So actually it is negative. You are predicting it as positive. So it is false positive. Actually, it is positive. We're telling it as negative. It is false negative. There are scenarios where your accuracy will be 95%, but you are having your 2 errors. These errors should be least. You may get very good accuracy, but your model is not good. Just like if at all you are having high R square, you cannot say that your model is good. Just because your accuracy is 95% for logistic regression or any classification models, we cannot say your model is good. You want your false negative values and false positive values as least as possible. Right? So that is the evaluation metric for your logistic regression. That is the evaluation metric for your logistic regression. So similarly, now when we talk about evaluation metrics, right? How can you say that your model is good for linear regression? You are calculating R square, you are calculating adjusted R square, right? You are checking the overfitting or not, you are checking R square, you are checking this correlation, not R square. Can we say, because we're looking into one particular aspect, can we say that this model is good, this model is bad? It is not one parameter we look for linear regression. So bunch of things have to be compared, assumptions should be satisfied, then only you can say that your model is good or bad. Okay. Okay. Now, when we are talking about ordinal logistic regression or multinomial logistic regression, they are different variants of logistic regression. So when we talk about discrete data, discrete means you have your count and also you have your categorical. So again, categorical means you may have ordinal, you may have nominal, right? So the process here is the same for the other two models also. So it is a classification algorithm. You are doing classifications just because it is under this. So it is binary logistic regression, or it is multinomial logistic regression, or it is ordinal logistic regression. So the main intuition is that your regression equation is a problem there and you are not getting the best classifications. So what you have to do? The decision boundary is very, very important. Now, do you think outliers impact is there on logistic regression? So outliers, impact of outliers. On logistic regression. Definitely the estimates, whatever you are getting, they are sensitive to different, I can say, unusual observations such as outliers or what we call it as influential observations. Therefore, to solve the problems of outliers, a sigmoid function is something which we are using to solve the problem here in logistic regression. Right? So which algorithm is better if at all outliers are there in your data, will you go for SVM or will you go for logistic regression or any other? Algorithm will do good if at all you have more number of outliers. Achha, chalo, we can discuss compare between SVM and logistic. You know, SVM is a black box, we can say, and you know, it does a better classification than logistic, because logistic regression, it is identifying a linear boundary if it exists to accommodate the outliers. To accommodate the outliers, it has to shift that the classification linear boundary. But this SVM is insensitive to the individual samples. So there will not be any major shift in the linear boundary. It is built in such a way that it is designed in such a way that it comes with inbuilt complexity controls, which will not only take care of this overfitting, which is not going to happen in logistic regression, right? Which is not going to work here in logistic regression. So for any reasons, people prefer classification models only, but because of the interpretation what we get for logistic regression, like null deviance or residual deviance, people are still preferring logistic regression also for classification. Right? So it is very easy to understand, and you know, it is very less training data, less training is required for logistic regression, right? It does not make so many assumptions, and it's very rarely we can see there is a chance of overfitting. Yeah, definitely overfitting happens when it is a high dimensional data set. If at all it overfits for high dimensional data, we have anyway discussed about the regularization technique for regression models. So very efficient to train. It is very easier to implement and interpret. And the only thing what we feel it is difficult with logistic regression is that lot of feature engineering is required. Right? It is quite sensitive to noise. If it is high dimensional data only, it overfits. Right? So these are few things with respect to regression. So thank you all for joining in. Thank you. Have a great Sunday.